All right, welcome to chapter 3, where we're going to kind of evolve with the idea of our limits that we found in chapter 2. So again, everything in math builds, so we have to learn something to be able to go on to the next step. So here we go with the idea of derivatives as a function. Now that we are familiar with limits, we will evolve into one of the fundamental topics of calculus, which is derivatives. The derivative of our function f, get my pen going here, is another function that's actually denoted by f prime that gives the slope of the curve y equals f of x as it changes with respect to x. That's a key idea that you want to remember. Equivalently, the derivative of f also gives the instantaneous rate of change of the function f with respect to the independent variable, which most often than not when we talk about rate of change is going to be time, because we're looking at positions of things and velocities and such. Limits are used to define derivatives, and so we had to know how to do limits first, and then we can define derivatives, and the applications of derivatives are endless because almost everything around us is in a state of change, and derivatives describe change. So if you recall in chapter 2 when we talked about the average velocity and the instantaneous velocity, we had these charts that looked at what these values were getting closer and closer and closer to, and we said that it merged or limited to a number, and we call it the instantaneous velocity. And so that's where we're going to kind of evolve. That's where a couple things come into play. The slope of a tangent line and the instantaneous velocity is going to come from these derivatives. So in this section, we will be doing more problems of finding the slope of a tangent line. And this problem is important for several reasons. So we're going to ID the slope of the tangent line with the instantaneous rate of change. The slopes of the tangent lines, as they change along a curve, are values of a new function in which we're going to call a derivative. And if a curve represents the trajectory of a moving object, the tangent line at that point on the curve indicates the direction of motion at that point. Okay? So, a couple little pictures here just so you can kind of see a couple of these ideas. If I draw, say, some parabola that looks like this, and I change my color here to create, say, maybe to this point, I have a line that is tangent. Recall that a tangent line only intersects my graph in one spot. If I also maybe choose this point and I do a line of a tangent at that point, then we have a couple examples there of lines that are tangent to our curve. Now, this has a slope that is positive, and this has a slope that is negative. So you always want to kind of keep an idea of our slopes. Now, if I have kind of a motion for an object or a trajectory, I may have a curve that models its motion like this. I could also create some lines that are tangent to this curve. Say maybe at this point, a line tangent would look something like that, and my slope in that case would be positive as well. But if I choose a point over here and I look at the slope of the tangent line at that point, this one is also going to be negative. Now, there are certain points also in which we may have slopes that have a no change at all, which is slope of 0, a horizontal tangent line, and those are going to be important as well. Okay? So, recalling from section 2.1, I just kind of spoke of these with the average velocity and the instantaneous velocity. The average velocity, if you had some function s, which represented the position, hopefully you recall on an interval of from a to t, we took the position at the largest point minus, or the later point, minus the initial s of a and divided by t minus a. And so that's how we calculated the velocity, the average velocity, over a certain interval. Now, this equals the slope of a secant line. A secant line, don't forget, is one that intersects a graph in two places. And so the instantaneous velocity at A is now bringing in the idea of calculus, where we are limiting as our t value goes to A, of exactly what we have over here for our average velocity. So S of t minus S of a all over t minus a. And so here's the idea of that calculus part. If we end up finding the instantaneous velocity at a, that is the same as finding the slope of the tangent line at a. So you got to keep reminding yourself that those two things are equivalent in nature, that the limit here to find the instantaneous velocity is the same as the slope of the tangent line and same as the average velocity with the slope of the secant line. So let's look at kind of a projectile motion problem here. It says that a rock is launched vertically upward from the ground at an initial speed of 96 feet per second. The position of the rock in feet above the ground after t seconds is given by this function. So this is my position function at any time t. I can choose any time t, plug it in, and that would be how high the projectile is. Now, consider the point at 180. If I put 1 in there, I'm going to get 80 to kick out, okay? That is a point on this curve. Now, we are asked to find the instantaneous velocity of the rock 1 second after we launch and find the slope of the tangent line to the graph of S at P. So if I'm going to find the instantaneous velocity, I'm going to use this formula right here, okay? So velocity of instantaneous is going to be found by taking the limit as t goes to, now where are we looking at? We're looking around 1 second. So as t goes to 1, so our a value is 1 here. This is a, okay? So we're looking at putting a in there. We're going to go S of t minus S of 1 all over t minus 1. So I just kind of started that to get you set. So let's fill in S of t. Limit as t goes to 1. Remember, don't drop off your limits. S of t is this function, so I'm going to go negative 16t squared plus 96t. And then minus S of 1. Well, I can put 1 in there, but we already know what 1 is by stealing from this point over here. So I want to subtract 80 from that, all over t minus 1. Now, if I plug t minus 1 in the top, I'm going to get 80 minus 80. Because if I plug 1 in there, I get negative 16 plus 96 is 80. Minus 80 is 0. Plug 1 in the bottom, I get 0 as well. So 0 over 0 means I need to factor my function a little bit to see if I can get rid of that factor that's giving me the 0 over 0s. So up top here, I do have a common 16. And actually, I'm going to take out a negative 16. And when I do that, I'm left with t squared minus a 6t plus a 5. All over a t minus 1. Oops, I forgot to put that we're approaching 1 over here. Okay. Now, can I go further? Again, if I start plugging in 1, I'm going to get 0 over 0. So I'm going to try to factor this piece right here. And I'm going to kind of just save a little space and factor it up top. So when I do that, I'm going to get a t and a t. The signs are the same that match the first. So minus and a minus. What do we multiply to get 5 that I add to get 6? And it is a 1 and a 5. So this factor now will cancel with that factor in the bottom that is exactly the same, leaving me with the limit as t goes to 1 of negative 16 times a t minus 5. And that's my new function that hopefully when I plug in t equaling 1, plug in the a value, that I do not get 0 over 0. Well, because these cancel, we will not now. So when I plug in negative 1, then my limit is equal to negative 16 times 1 minus 5, which is negative 16 times a negative 4. Therefore, I get a velocity here, instantaneous, of 64. Now, our units, we were in seconds and we were in feet. So for velocity, it's like speed, except for it has a direction added on it. We have 64 feet per second. Now, the second question there says, find the slope of the tangent line. But remember, these two things are equivalent. They're the same. So if I were to look at the point 180 for this function, then the slope of the tangent line is going to be 64 as well. Okay? So, making sure that you know how to equate those. All right, now the last little piece here on this problem is, and we're going to do this quite a bit, is to write the equation of the tangent line. Okay? So what do we need to write an equation? Well, given point slope form, which is what I recommended you to use, which is this, y minus y1 equals m times x minus x1. I need a slope and I need a point. Well, the slope is 64. The point is this 180 back here that I have. So I'm going to go y minus 80 equals my slope, which is 64 times x minus 1. And from here, getting it into y equals mx plus b is good. Actually, I probably shouldn't use y and x. I should use t because we're working in time, but that's okay. We're going to go ahead and just solve this, and we can change the variables later. Whoops, that's the wrong one. Undo that. Sorry, I need to distribute the 64. So we get y minus 80 equals 64x minus 64. And then I add over my 80 with the negative 64, and I get y equals 64x plus 16. And so, again, we are in terms of s and t. So here I have, I'm going to replace that with t. So you could just say that, well, here nor there. It doesn't really matter. On my paper, I wrote y equals 64t plus 16. So the independent variable here is t. Dependent is s. It doesn't matter. Okay, but this would be what our equation of our tangent line would equal. Okay? All right, very good. Let's go to the next page. And we're going to evolve into some definitions here that are going to help us to find the derivatives of our functions. And so here, for this first section, we're actually just finding derivatives at a point, and then we will evolve into the actual functions. So here I have the average rate of change in f on a closed interval of a to x is the slope of the corresponding secant line. Remember, average rate of change, average velocity was the slope of the secant line. So the slope of the secant line for our function f is going to be defined as f of x minus f of a all over x minus a. So a rate of change, basically y minus y over x minus x, to find a slope. Now, that's important because when we now turn to the instantaneous rate of change in f, that is where we bring into the calculus, which is actually going to be, I'm going to do m of tangent because this is the equivalent to the slope of our tangent line. Now we take the limit as x approaches a of this slope of our secant. So f of x minus f of a all over x minus a. Now I'm going to ask that you star this because this is what they use in your book as definition number 1, okay? Or box it in, star it, whatever you want to call, whatever you want to do. So this is also the slope of the tangent line at the point a comma f of a, provided that that limit exists, okay? So that's one of the definitions that you'll be using for the limits in finding a derivative of a function at a point, okay? So maybe I'll do this so we can still see that. Find the equation of the line tangent to this function when x equals 2. So I'm going to take that definition that we have up there, definition 1. The slope of the tangent line is equivalent to the limit as x approaches, our value is 2 here, of f of x minus f of 2 all over x minus 2. So that's where I'm starting from this guy right here. Now, at this point, I'm going to now plug things in that I know. So I'm going to keep my limit as x approaches 2. Don't be lazy and drop that. F of x is equivalent to 3 over x. So I do 3 over x minus f of 2. So if I take 2 and plug it into my function right here in the denominator, I get 3/2 as that number. And I'm going to divide that all by x minus 2. Now, if I try to put in 2, I'm going to get 0 over 0, so we've got to do a little bit of finagling of this function. Now, this function is finagling in order to, I got to get it's a complex function, so I need to end up getting one fraction basically. Now, finding the equation of the line tangent to, I should have prefaced with that, to find the equation, I need a point and a slope. So here's where I'm going to get the slope of the tangent. We'll worry about the point here in just a second. All right, so back to simplifying this. We need to do the limit as x approaches 2. Now I'm going to get a common denominator up top here. And that common denominator, I need an x and I need a 2. So I need a 2x. Well, in order to have a 2, I need to multiply 2 here, top and bottom. And I need to multiply top and bottom here by x. So the top piece becomes 6 minus 3x. And all of that is over the x minus 2. And I could put that over 1 to get a fraction over fraction if I wanted to. Now, this is where you could do one of two things. You can rewrite this and multiply by the reciprocal of this when dividing two fractions. Or if you are one that knows about extremes over means, in order to take the product of the extremes over the product of the means, you can do that as well. That's what I'm used to, so that's what I'm going to do. But again, you can rewrite the first fraction and multiply by the reciprocal of the second when dividing those two fractions. Okay, so 6 minus 3x times 1 is still just 6 minus 3x. All over the product of these two, so the best that I'm going to write is just 2x times an x minus 2. Now again, if you try to put 2 in here, you're going to get 0 over 0, so I still need to work a little bit. In this case, I'm honing in at the top, and I'm saying, oh, well, that kind of looks like I might be able to factor a common term. To make me kind of get rid of this x minus 2, I should have an x minus 2 up here. So I'm going to take out a negative 3, and when I do that, I'm going to kind of reverse these orders. Negative 3 times an x gives me negative 3x. But when I take out a negative, this sign's going to change, and I need a 2 to make the 6. So that should be what I have when I factor out a negative 3. And that's very nice because now this and this cancel, eliminating the idea of that 0 over 0. So now I get the limit as x approaches 2 of negative 3 all over 2x. And that's how I have to find my limit. So now I get to plug a in. There's now no 0 over 0, so I'm good. I get a number. When I plug a in right here, I get 4 in the denominator with the negative 3 on top. And that right there is my slope of my tangent line. And that's what I need, along with a point, to find the equation of the line tangent to our graph. Now, before, on the reverse page, they gave us the point 180. Here, all I know is that x equals 2. Well, if x equals 2, I have to find the matching y value. And how do I do that? Well, I have this function here that aids me in doing that. I'm going to plug 2 in, and the y value is going to be 3/2. So the point that I have here that I'm going to use in the equation of my the equation of my tangent line is the point 2 3/2. So I'm going to take this point and this slope and write the equation of the line tangent. So here we go. We're going to go y minus the y value, which is 3/2, equals my slope, which is negative 3/4, times an x minus the x value, which is 2. And from here, it's just basically algebra, distributing this through and adding over 3/2. So I get y minus 3/2 equals negative 3/4 x. A negative times a negative is going to be a positive. And when I multiply 3/4 times 2 over 1, think of it that way, those 2's are going to cancel, leaving me a 2 in the bottom. So I'm going to get a 3/2 over here as well. So when I do that, and I add over my 3/2 to this other side, I'm going to get negative 3/4 x. And when I add 3/2 to 3/2, keep the bottom, so I'm going to keep the 2 and change the top, which is a 6. So if you wanted to, you could write that as a 3. Actually, you should write it as a 3. So y equaling negative 3/4 x plus 3 will be our final answer for the equation of that line that is tangent to the curve. Okay? All right, very good. So, our next rate of change, which is actually what they refer to as definition number 2, is going to be very similar, except for it's just a different form. So this looks the same. Average rate of change in f on a closed interval, a comma a plus h. So instead of having a comma x, now I'm just adding a small little amount to where I start with this plus h. So that is the slope of the corresponding secant line. And we do this by taking y minus y of our endpoints over x minus x. Okay? Now when I do that, what I'm proving basically kind of here to you is that these a's are now going to cancel out. So this is f of a plus h minus f of a all over h. And so that is the secant, slope of the secant line. But we're looking with derivatives for the instantaneous rate of change in f at a. Now we get to do the slope of the tangent line, which is basically taking the limit that I have here. Now, the limit now is going to be when h goes to 0. So if h is this very, very small amount that I'm adding to a, what happens when I get that very, very close to 0, where we're very, very, very close to a? Well, this is our definition. F of a plus h minus f of a all over h. And hopefully you recognize that. I'm going to box that in because that's important. That's what they refer to as definition number 2 right there. So this is a difference quotient that you saw in chapter 1 and 2 that we were working with. So that's why it's important to practice that. So again, this is also the slope of the tangent line at the value a, f of a. Provided again that that limit does exist. Okay? All right. Very, very, very good. So here we go. Here's another type of, just a regular type of problem when you start working with derivatives, is find the equation of the line tangent to the graph. So you have to take the limit for the derivative in order to find the slope of the tangent line. This represents the slope of the tangent line. Here's our function this time. It is a cube, and now we're doing it when x equals 1, okay? So let's go ahead and figure out what the point that we have here. If I plug 1 into my function, what is f of 1? Well, I do 1 cubed is 1, plus 4 times 1 is 4, so that gives me 5. So the point I'm working here with is the 0.15. They may give you the point, but you may also have to establish that on your own. All right, so here we go. Slope of the tangent line is found by taking the limit. We're using definition 2 here. So as h goes to 0 of f of, now a this time is 1. That's the one value that I have. So I'm going to have f of 1 plus h minus f of 1 all over h. So again, we're working with these derivatives at a certain point now. If later on we will evolve into just the function of what it is. All right, so I'm going to take this 1 plus h and throw it into my function wherever I see an x. So just this piece is 1 plus h cubed plus 4 times 1 plus h. Now that is just f of 1 plus h, so make sure you do it correctly. Minus, what is f of 1? Well, it's nice that we just did that over here, so I know that that value is 5. You could do it again if you wanted to, but no need to. We'll steal it from there. All right, what's hard about this problem is the very first thing that we're going to have to do to simplify that, and that's this piece right here, okay? So I want you to make sure if you need to go off to the side, let me see if I can scoot down a little bit. Go off to the side and see if you can multiply that. Now, there's certain ways you can do this called a binomial expansion, but if you're not used to it, we're going to write it out 3 times and FOIL it. Okay, so 1 plus h cubed is actually this. If you know the binomial expansion pattern, it's much easier. So I'm going to multiply this first. So I get first, which is 1. Outside is h, inside is another h, so I get plus 2h plus h squared that I now have to multiply by a 1 plus h. So I'm going to take 1 times each of those, so I get 1 plus h. Then I'm going to take 2h times each of those, so plus 2h plus 2h squared. Then I'm going to take h squared and multiply by both of these. So basically you're just doing a binomial times a trinomial distribution. So I get another h squared plus an h cubed this time. So if I were to combine all of this together, I get 1 plus 3h squared plus h cubed. Whoops, I forgot my limit on this one. If they don't be lazy and drop it, and I dropped it. So we're going to carry our limit through. And I'm going to rewrite what our 1 plus h cubed is equivalent to from what we found down here. So that was 1 plus 3h plus 3h squared plus h cubed. And now I have to also come back here and finish off this bracketed expression by distributing the 4. So I get plus 4 plus 4h, but I also have this minus 5 all over h. Now, let's see what happens here. You should get a lot of stuff that cancels. If things don't cancel, you've done something wrong. Okay? So, I'm going to cancel here with the 5 and the 4 and the 1. Those go away. And I don't think anything else cancels. Now, I can combine some stuff here, but I can't cancel it. So, I'm going to come down here and say, all right, the limit as h goes to 0. What I get is, I'm going to rewrite with the h cubed first. So I'm going to go h cubed in descending order plus 3h squared. And when I combine 3h and 4h, I get plus a 7h all over an h. Now notice, each one of those terms have an h. So if we're going to cancel, we have to cancel an h with all 3 terms, or however many terms that I have up here, which I can do. So we're going to go the limit as h goes to 0 now. When I cancel into here, I am left with 2, so an h squared. Cancel 1 here, leaves me a 3h. And then the h is canceled with the 7, so I'm just left with a plus 7. And now's the time that I get to calculus and plug that a value in, which is 0, and take the limit. So if that's 0, that means that's gone and that's gone. Therefore, my limit is 7. Now, what did we find? Again, that's the slope of the tangent line. So you've got to make sure that you're looking at this being our m. With the 0.15, now we can write the equation. So I'm going to go y minus the 5, which is my y value, equals the slope, which is 7, times x minus 1. And again, get y by itself, which should be pretty easy. That's some Algebra 1 stuff. 7x minus 7 when I distribute. And when I add the 5 over, then I get y equals 7x minus 2 as the equation of the slope of the tangent line for that function when x equals 1. That's what we found. Okay? All right, very good. So on our last page, it just kind of sums it up for this section, okay? So if we turn to here, here's where our kind of our definition of our derivatives, and if you want to kind of just work with this box here to remind yourself of what we have, then that's important because it will put both of them together. So here's where we're defining that the derivative of f at a point A, which is denoted by f prime of A, and it's red, f prime of A, is given by either of the two following limits, provided that the limits exist and A is in the domain of f. If it's not in the domain of f, it's not going to exist. So here's one. F prime of A can be the limit as x approaches A of f of x minus f of A all over x minus A. And this is what they refer to as your definition number 1. Or we also found that f prime of A is also equivalent to the limit as h goes to 0 of f of A plus h minus f of A all over h. And this is what your book refers to as definition number 2. So in your homework on My Lab Math, if they ask you to use each one of those, or if I ask you specifically on the test to use one, then you want to make sure that you are able to do that. Okay, so if f prime of A exists, we say that f is differentiable at A. Okay? Differentiable means that a derivative exists at that point. So the limits that define the derivative of a function at every point are exactly the same limits used to compute the slope of a tangent line and the instantaneous rate of change of the function. So you have to remember that the derivative kind of finds two things. One of them is the slope of the tangent line, and it is also equivalent to the instantaneous rate of change. So if you're asked to find either one of those, you are asked to find the derivative of that function. You got to remember that those two things are exactly the same. So let's try this guy here. We're going to compute f prime of 2 and use the result to find the equation of the line tangent to the graph at 2, 3. So we already have the point. That's nice, because when I'm writing the equation, y minus 3 equals, I'm going to leave a space for my slope, x minus 2. All I need to now fill in is this piece. And how do I find that piece? What is the slope of the tangent line? It is the derivative. And to find the derivative, I have to use either one of these limits that are in this box up here. And in this case, we're going to try to use number 1 here, okay? So if I try to use the slope of the tangent line, which is f prime at 2, we are going to look at the limit as x approaches that a value of, we're going to use this version, f of x minus f of 2 all over x minus 2. And I'm going to plug in f of x, which is this radical equation right now. So we have the limit as x approaches 2 of the square root of 2x plus 1 minus, so that's f of x. Now, what is f of 2? Well, you can plug 2 in here if you want. But if you want to, you can just grab it off of here. This is f of 2. That's 3. So I'm going to subtract 3 all over an x minus 2. Now, if we try to plug a in, you're going to get 0 over 0. This is one that I'm probably going to have to rationalize, okay? So we're going to say the limit as x approaches 2. I'm going to rewrite the top because I'm going to take 1 minus 3 and get a minus 2 all over an x minus 2. Now, this is where you want the conjugate to come into play. When you have radical functions, we have to rationalize where that radical is. So I get the square root of 2x plus 2 is what I would multiply top and bottom by. And I'm also going to put the parentheses around that bottom. All right, so we get now the limit as x approaches 2. Now the top becomes a difference of squares. All I have to do is you can FOIL, but the outside inside is going to cancel. So I multiply square root of 2x times square root of 2x is just 2x. Outside is going to cancel with the inside, so then I need the last term, which is a minus 4 all over x minus 2 times the square root of 2x plus 2. Now, again, something's going to have to cancel, and I'm looking right up here at this 2x minus 4, and I see, oh, well, I can take a 2 out. And if I take a 2 out, I'm left with 2x, or 2 times an x minus 2. Therefore, this and this go away and leave me now with the expression that I can plug my a in. So I get a 2 on top all over that conjugate, which is the square root of 2x plus 2. So what happens when I throw 2 in there? Well, obviously in the top we're still going to be at 2. When I plug 2 in here, 2 times 2 is 4. The square root of 4 is 2, plus 2 is a 4, so it looks like I have a slope of 1/2. Okay, so a lot of work. You got to know how to do those limits before we can now apply within our difference quotients here to plug in to find our equation. So we have 1/2 being there. So therefore, my equation of my tangent line is going to be 1/2 x, and then 1/2 times a negative 2 is a minus 1. When I add over the 3, I get 1/2 x plus 2. And that is the equation that we need there for that. Okay? All right, very good. And last problem that we have, the last problem is that you're actually just kind of looking at graphs and determining what is f of 3 and f prime of 3. So remember, this is the function value at 3. This is the slope of the tangent line at 3. So these aren't hard. This isn't hard. It's just you got to make sure you delineate between what does f of 3 mean and what does f prime of 3 mean. So f of 3 is the function value. Here's my function. It's the parabola. This is the line that's tangent to that. So the value of my function when x equals 3, I come up here, that value is the y value at 1. So f of 3 is 1. But now when I look for the slope of the tangent line, that means I have to now determine by a rise over run from point to point, what is the slope of that tangent line? So I'm looking along this tangent line. There's another nice point on that. So if I go up 1, 2, and over 1, rise over run, I do get a value of 2 over 1, which is 2. So again, that is the slope of this tangent line You may need to graph 2 points if you want and do y minus y over x minus x, or you can look at it graphically as what your rise over run is as well. Okay? All right, very good. So that is our derivative at a single point, and having practice of doing that. What we will do in next section, we'll actually keep working with this, but now kind of look at the derivative as a function. And instead of just getting a value out for your derivative of a tangent line, we actually will get a function in terms of x. Okay? Until next time.